The variety of phenomena in the universe can be described by four forces: the strong nuclear force, the weak nuclear force, the electrical force, and the force of gravity. These are the fundamental forces of nature.
As we've gone along, we've been toying with a kind of philosophical enigma. The centerpiece of everything that we've done has been Newton's second law, which says that an acceleration is produced by a force acting on a mass. But aside from this equation itself, we have no idea of what force means, and we have no idea of what mass means. Suppose I told you I just made a great scientific discovery. I've discovered that gurgle snap is equal to quibble dunk times distance. Now you see, you're not impressed. And the reason is because I haven't told you what gurgle snap is, and I haven't told you what quibble dunk is. Well, the same is true of the second law. Unless I can tell you what force is and what mass is, the second law doesn't mean much. And yet, there's no doubt that we've been making progress. We've calculated trajectories and orbits, and we found out why all bodies fall at the same rate. Now, that's all good, solid stuff. It's not some sort of philosophical wordplay about gurgle snap and quibble dunk. And so how have we done it? Well, we've done it by introducing another theoretical idea, the law of gravity. The law of gravity is a clear, independent, explicit description of one kind of force. Every success that we've had has come not from the second law alone, but by putting the force of gravity into the second law. And so that raises an obvious question. The question is, what are the other forces? What are the fundamental forces of nature? That's the question before the House today.
The California Institute of Technology in Pasadena. At the Kellogg Radiation Laboratory, Charles Barnes and his colleagues probe the cores of atoms. They look into the very hearts of the stars. And with the Caltech accelerators, they observe nature's fundamental forces. Science and technology advance by quantum leaps. Yet even in the space age, Isaac Newton's equations are not forgotten. Here, for example, force equals mass times acceleration is alive and working well. In fact, F equals ma is the operating principle behind this accelerator, a machine the father of classical mechanics probably never dreamed of. And those who carry forward Newton's exploration perceive another operating principle of nature. Every bit of matter, everything from the outer edge of the most distant galaxy to the nucleus of an atom, is subject to four fundamental forces. In a complicated and confusing world, there are, or so it would seem, many different forces at play. Nonetheless, scientists have sought to reduce these to one, or at the most, to a very few. Two fundamental forces dwell within the heart of the atom. Another knows no boundaries in the cosmos. And the fourth holds all matter together. The fundamental forces in the atomic nucleus are called the strong nuclear force and the weak nuclear force. The strong force binds protons and neutrons into nuclei. It's so powerful it can overcome the natural repulsion of protons. And this power can be released in nuclear reactions. Indirectly, the strong nuclear force sets fires deep within the sun. and within other stars as well. And yet, as powerful as the strong force is, its range is so small that 12 zeros follow the decimal point to express it numerically as a fraction of a centimeter. The weak force, the other fundamental force within the nucleus, has effects that are by no means weak. Though its effects are subtle, they're very obvious. In the violent death of massive stars, for example, or in the decay of radioactive isotopes, a twist on alchemy that turns uranium into common lead. Increasingly, scientists are discovering how the nuclear forces link the past, the present, and the future of the universe. Yet, as much as is known about the strong nuclear force and the weak nuclear force, they remain somewhat mysterious. Hidden from the everyday world within the atomic nucleus, they remain among the innermost secrets of nature. The two other fundamental forces, equally wondrous and incredibly powerful, appear to be far less clandestine in nature, and they can be seen much closer to home. The most familiar fundamental force is gravity. Even in a commercial kitchen, the force of gravity accelerates mass. It came before both the chicken and the egg. But before Newton's law, people didn't know very much about gravity. They knew something about it, that it made things fall, for example, but they didn't know gravity makes the moon fall, nor that gravity, first and foremost, is a fundamental force of the universe. A fundamental force and an attractive force. As an attractive force, gravity can be described in popular human terms. Not only does gravity get around quite a bit, from one end of the universe to the other, it has considerable influence on everything under the moon. Far more than that, gravity relates to everyone and to everything. In a way, gravity reaches out and shakes hands with the entire universe. With his law of universal gravitation, Isaac Newton explained the how and why of gravity in the universe. How it pulls objects to Earth, and at the same time, why objects such as the moon stay in the heavens. He explained gravity in terms of force. And even though force is measured by a unit called the Newton, which gives credit where credit due, another Englishman shares credit for advancing science closer to the moon. He was Henry Cavendish, and he actually weighed the Earth. Chemist as well as physicist, he isolated a gas that became known as hydrogen. Cavendish was as reclusive as he was brilliant. Most of his work was published almost a century after his death. Nonetheless, in his own quiet way, he weighed the Earth in 1798. He weighed the Earth by measuring the constant in Isaac Newton's universal law of gravity.
Force is mass times acceleration, expressed in kilogram meters per second squared, or newtons. From the acceleration of a falling body and Newton's law of gravity, Cavendish already knew the mass of the Earth times g. To isolate mass from gravity, he had to measure the value of g. This could be done by finding the force between two known masses, a known distance apart. It had to be done very carefully because the gravitational force between normal-sized masses is so very small. A bar, suspended by a delicate fiber, holds a mass at each end. Two larger masses are added. The gravitational force between these masses causes the bar to twist. By timing the swaying of the bar, he could deduce the stiffness of the fiber, and thus the force. Switching the masses around makes the bar twist in the opposite direction, to correct for asymmetries in the experiment.
With this delicate experiment and a lot of care, Cavendish measured the gravitational constant and indirectly weighed the Earth. Weighing the Earth was an astounding accomplishment, but comparatively speaking, it's not truly shocking. The fourth fundamental force is electricity. Electricity seems the paradox of the forces. 1 minute exciting, raw, and even frightening in its power. The next, as ordinary as a pop-up toaster. On the bright side, electricity is as common as white bread. On the darker side, it conjures up images, some deadly, some mythical, and all of them somehow plugged into the character of Western culture. No image strikes closer to the American landscape than this Philadelphian harnessing electricity with a kite. Considering his unequaled accomplishments, editor and writer, inventor, politician, postmaster, and statesman, philosopher, the wit and wisdom of his era. Why has this image remained the most popular to this very day? Because Ben Franklin was young America's first and foremost scientist. In the course of studying its effects, Franklin had the ingenious but not quite accurate notion that electricity was a kind of fluid, an electrical fluid contained in each ordinary body. If the body held too much of the fluid, Franklin said it was positively charged with electricity. A body with too little was negatively charged. Franklin's terms, positive charge and negative charge, remain vital in the vocabulary of electricity. But the significance of the electrical force goes deeper than his reflections. At its most fundamental level, electricity is the force between positive and negative charges. It binds together everything in the universe, everything from soup to nuts, including the kitchen sink. Since that includes humans, why aren't they aware of the charges in their bodies? Why doesn't bread electrocute toasters? Every time people shake hands, why don't they fry each other like potatoes? Because everything has equal amounts of positive and negative charge for a perfectly balanced blend. Just as all matter is neutral, comprised of electrically balanced positive and negative charges, all matter is comprised of atoms. The atom's nucleus is made of protons, which are positively charged and illustrated in red, and neutrons in white, which have no charge. Negatively charged electrons, shown here in green, orbit the nucleus.
The electrical force is equal to the constant K sub E times the product of the charges, the Q's, divided by the square of the distance between them.
The formula for electricity is strikingly similar to the one for gravity. Gravitational force holds the 9 planets in orbit around the sun. The force is equal to minus a constant, G, times the product of the masses divided by the square of the distance between them. The natures of mass and charge are for the most part still unknown. But obviously mass is something that applies to gravity. Charge, something that applies to electricity. Since mass is always positive, gravity always attracts. Charge, however, can be either positive or negative. A positive and negative charge will attract. Two positive charges will repel, as will two negative charges. Otherwise, just as their formulas state symbolically, gravity and electricity are so much alike that an atom, with a little rearranging, looks almost like a little solar system. When scientists discovered that two of nature's four fundamental forces are almost the same, a logical question arose. Could there be one force that alone explained the fundamental nature of everything in the universe? Thus began the ongoing journey toward this single unified theory. And for the last 20 years of his life, Albert Einstein wheeled along this difficult path of research. Even though Einstein never reached his goal, the search continues and the findings suggest great promise. Found in the debris of nuclear collisions, these fragments suggest a deep underlying connection between the electric force and the weak nuclear force. Nevertheless, outside the realm of ongoing scientific research, the world of common experience continues to be governed by ordinary gravity and electricity. Gravity. It's the force that makes some objects fall, keeps others from spinning off the face of the earth. Gravity. It keeps the moon orbiting the earth and the planets orbiting the sun rather than wandering in space. Electricity. Just as gravity binds the planets to their appointed rounds, electricity binds atoms and molecules into liquids and solids that create everything from the most complex organisms to the most ordinary table salt. Although ordinary matter is electrically neutral, the atoms deep within can be both negatively and positively charged. Salt illustrates how these charges can hold matter together. Salt crystals are bound by the electric force between positively charged sodium and negatively charged chlorine ions. Electricity, in countless forms, is a fundamental force that constantly springs to life. For instance, the spring action of a metal object is actually an electrical process. Metal ions, which are positively charged, are glued together by electrons, which are negatively charged. Stretching the metal pulls the ions apart, but the electrons force them back together. Another form of the electrical force is friction. When two objects come into contact, their positive and negative charges interact, and their surfaces are, at least temporarily, bonded together. A third form of the electrical force is viscosity, which determines the rate at which fluids flow. For example, each of these beakers contains a fluid with a specific and different viscosity. The more viscous the fluid, the more slowly an object will fall through it. As with the actions of a metal spring and two objects creating friction, viscosity is a result of the electrical charges of their atoms. Here, as the objects make their way downward, liquid molecules flow around them under the influence of the electric force between them. 3 centuries after Isaac Newton's genius produced F equals ma, Professor Barnes and his colleagues used the electrical force to accelerate mass. The Caltech accelerator is used to recreate events that occur within the sun, smashing nuclei together at high speeds to make them react. A negative ion is an atom with an extra electron attached to it. When it's injected into the accelerator, it's drawn toward the positively charged high voltage terminal. This is a powerful attraction, and it's due to the electrical force, the force between the negative ion and the positive charge on the high voltage terminal. Inside the chamber, there's a tube through which the ion will pass. Halfway along the tube, there's the high voltage terminal with a large positive charge. Meanwhile, at the beginning of the tube, a carbon atom gets a negative charge. At the same point, another negative charge pushes the ion along its way. One magnetic field steers the ion around the corner. While another keeps it at the center of the tube. Seeing the positive charge just up ahead, the ion feels attracted and accelerates. In the most positive region, a few gas molecules lay in wait. The ion inevitably hits a molecule, and the collision strips off some of its electrons. Now the ion's charge becomes positive, and since this is no place for a positive charge, the ion has a terrific urge to escape, and as fast as possible, it does. Not only fast, but incredibly powerful. In fact, within this accelerator, the ion reaches energies even greater than those at the center of the sun. How is that possible? Because these scientists used the same high voltage twice. First, it was used as negative ions accelerated toward the high voltage terminal. And the voltage was used a second time as positive ions accelerated away from the terminal back to the ground potential. The idea of using the same high voltage twice was at first considered unorthodox, even bizarre. However, working well within the laws of the physical world, a tandem accelerator makes perfectly legitimate and double use of the voltage. The tandem accelerator has become a standard tool of experimental physics. This experiment, for example, is an attempt to find out how rapidly carbon nuclei fuse with helium nuclei to build oxygen. Carbon ions are directed through an evacuated beam pipe toward the target, helium. This nuclear reaction determines the relative amounts of carbon and oxygen, a crucial step in the evolution of the stars. And by taking such steps, physicists approach not only the stars, but a greater understanding of the universe at large. Success? Yes, in the relative one-step-at-a-time sense of experimental physics. The next earthly step toward the stars, and certainly not the last. Scientists will continue to probe the secrets of the stars, and they'll be able to unravel the mysteries of the cosmos, because they know what Isaac Newton was the first to understand. The fundamental forces of nature are the same for all matter in the universe.
All right, we've done what we set out to do. We've enumerated the forces of nature. But we've also learned something subtle and far-reaching about the nature of physics itself. Let me explain. Before Isaac Newton, the science of physics as we know it did not exist. The difficulty was not that we didn't have all the answers. The difficulty was that we didn't know what questions to ask. Of course, a genius like Galileo could make progress essentially by making up the rules as he went along. And there were those who thought the situation was well in hand. René Descartes thought we would understand everything in a few years if only we would follow a few rational principles that he was gracious enough to lay out for us. But he was wrong. Our knowledge of the universe was in a state of chaos, and we didn't even have a clear idea of what questions would have to be answered in order to get anywhere. And then along came Isaac Newton, and he said F equals ma, and the mist started to clear. Why? Because we can calculate accelerations? Obviously, that's not the point. The real point lies at the heart of that enigma that we were discussing earlier. If this equation is to be the keystone of our understanding of the universe, then we must know what forces there are, and we must know what matter is. But those are clear questions. The questions are, what are the fundamental forces of nature, and what are the ultimate constituents of matter? Those are the questions that Newton's law focuses our attention on, and they are, to this very day, the central problems in all of physics. And we'll get on with those problems next time.
The strong force and the weak force dwell within the nucleus of the atom. Awesome, but comparatively mysterious. The other two are better known and seemingly more pervasive. Gravity is the most important force between objects that are very far apart, and the atoms and molecules of all common matter are bound together by the force of electricity. The weak force, the strong force, gravity, and electricity. These are the fundamental forces of nature.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.